Today we will be talking a little bit about another aspect about solids. So far we have studied in some detail the motion and the properties that arise from the motion of electrons, both from the classical and quantum mechanical point of view. And we have always treated the lattice as if it was basically completely rigid. So when I draw, and let me just draw it one-dimensionally in this case, when we draw the lattice, we think of a series of points that are in fixed positions, and these positions represent the positions of atoms or molecules, whatever forms your periodic lattice. And we have always modeled what happens to the electrons that are immersed in this periodic structure. However, the periodic structure, the nuclei themselves, or the molecules, whatever the lattice centers are not actually completely fixed. I mean, there are a series of forces that more or less keep them in place, but they can still move a little bit around. So let's think of atoms, but this could be molecules as well, or something complicated. But let's think just for a moment individual atoms. And these atoms can actually move around their positions a little bit and vibrate and so on. And this is something that we haven't really discussed. So this is what we will target today. And just for a little making it a little bit more complicated, I will introduce two types of atoms. So we will have a lattice that combines two types of atoms which are of different masses. So we have a lighter atom and a more massive atom, and in principle we think of an infinite chain in both directions, and we will think of this atom to have a mass m1, and this other atom to have a mass m2. Okay, and from that we will try now to understand how phonons happen in these periodic systems. And phonons are basically the quantum mechanical view. But there's also a classical phonon, so to speak. But it basically gives us the view of the collective vibrations in these atoms. Okay, great. So what we will now try to model is how these atoms are restrained to stay more or less within their equilibrium positions. And the simplest model we can adopt is thinking that these atoms are bound together by springs. So we can just imagine that we have springs binding these atoms with their closest neighbor. And of course, we know that this is not true. I mean, there are no springs in real lattices. The truth is, it's more complicated combination of electromagnetic forces and repulsions and attractions between the particles. But as long as the perturbation is small, and if there is an equilibrium position, which we know there is, the essence behind this idea is correct, because any potential with a minimum can be approximated within certain range as a harmonic oscillator, and we all know that as a parabolic potential. So essentially, using this harmonic approximation, what we can do is we can try now to write down the motion equations for these two types of atoms. And the first thing I want to make clear is that we will assume that this lattice is infinite. So we have this period that I will draw here, this period here, repeats indefinitely in both directions. So The unit cell is well defined, and that's the unit cell essentially. And then what we have now is that regardless of in which specific atom or in which specific unit cell of the crystal you're standing, basically, if you look to the left or to the right, you essentially see the same. It's an infinite chain of atoms in both directions, so you cannot distinguish between one side and the next one. So more or less, it doesn't really matter if we are in the nth or in the n+1 or the n-1 site. The only thing that matters is the interaction between the atoms with the next neighbors, and that's it. Okay, that being said, let's try to write the motion equations for these two atoms, and I will grab this atom over here and this atom over here, and let's try to see how. So classically, what we have is that the force on each one of the masses will be proportional to the mass and acceleration they're subjected to. So essentially, if we look, for example, at this mass over here, what we will have is that m1, the second derivative of its position, which we will denote as u1 of s times a, where s times s is an integer number that just refers to the lattice side, and a is the lattice constant. So it refers to the est position in the lattice. Will be equal to minus k, where k is the spring constant that we're using. So this is the k, and times 2u1 of SA, which is the position itself, and the distance to the first neighbor. So we will look at the first neighbor on the right, which is minus u2 SA, and the first neighbor on the left, which is minus u2 s minus 1 A. And same applies to the other mass. So now we are looking at this mass. The equation of motion for that one will be m2u double derivative to SA will be equal to minus k times the distance to its first neighbors as well, which is going to be 2u2 SA minus u1 SA minus u1 S plus 1 A. And just to try to solve this quickly, we can assume that the waves that would represent these, that will model the motion of these atoms are just plain waves. So what we obtain is, we can assume that U1 is equal to, A1 of SA of SA comma T will be equal to some amplitude E1 times E to the I, and we use Q here instead of K, just because that's the usual notation we use for phonons, but it is a plane wave just like any other plane wave we've seen before, SA minus omega T, and we will have that U2 will be equal to E2 e to the minus e to the I, sorry, yeah, to the I, e to the I q s a minus omega t. Okay, and from there, in order to have, so if we plug these two into the equations in the previous two lines, we need to impose, I mean, for this to have a solution, I mean, putting these solutions in the two differential equations, convert them into algebraic equations, and in order to have a solution for these algebraic equations, we need to impose that the determinant of the system equals 0. So what we obtain is that 2k minus m1 omega squared minus k1 plus e to the I q a minus k 1 plus e to the I q a 2k k minus m2 omega squared, the determinant is equal to 0. Okay, so from this determinant, what we obtain in the end is the following equation: that's 2k minus m1 omega squared 2k minus m2 omega squared minus k squared times 1 plus e to the I a q 1 minus e to the I a q equals 0. And from solving this equation, we obtain two possible solutions. So omega squared plus minus, which we will call r k times 1 over m1 plus 1 over m2 plus minus k times the square root of 1 over m1 plus 1 over m2 minus 4 times sine squared of q a over 2 divided by m1 m2. Okay, the important thing I want to stress here is that we actually have two solutions, and what this means is that for every q there will be two possible omegas, and this gives rise to something that we will discuss in just a minute. But initially, let's focus on the approximation for small q's for each one of these two cases. So when q is very, very small, and we take the minus sign, basically this term over here, and this term over here, which is missing for, right, by the way, a square there. So these two terms, this term here and this term here, basically cancel each other, and we just get something that goes for small q's as sine squared, the square root of sine squared of qa over 2. And that, again, within the small q approximation, can be written as, omega minus will be approximately the square root of k divided by 2 times m1 plus m2 q times a in the linear approximation of sine. And the other one, the other solution, the one that is plus, basically the addition of this term and this term essentially cancel each. Sorry, they are much bigger than this one. Okay, in the case of the addition. So the addition of these two terms is basically much bigger than this one, and what we end up with, again, in the small q approximation, is that omega plus will be approximately equal to 2k m1 plus m2 divided by m1 m2. Okay, and this means that again, in the vicinity of q equals 0, q was the equivalent to the wave vector, is the wave vector of this collective oscillation of atoms in the crystal, which now we know, because it solves the equation, it behaves like a plane wave. So the phonon, these vibrations of the lattice, produce plane waves that propagate through the crystal, something similar to what happens in the case of electrons. And we essentially get two possible solutions in the vicinity of q equals 0, which we can draw like this. So let's put here q, and let's put so in the vicinity of the 0q region, what we get is something that basically looks linear in both directions, and the other solution is somewhere here, and it basically looks more or less constant with this value. Of course, we would have to make a plot of this full equation of the two solutions in order to know what the solution really looks like. And what we obtain in that case, let me get a new page. So the dispersion relationship, the full relationship, dispersion relationship that relates the wave vector q of this phonon, of this plane wave that propagates through the lattice, with its frequency, looks something like that. So it's more or less linear, and then it bends a bit, and it produces a more or less a piece of a sine wave shape, and this is up to pi over a. And in the other direction we get something very similar, so we have minus pi over a here, and we get something that is like that. And the other part that looked constant here in the vicinity of 0 does something that looks a little bit like that. So it's a curve, does something like that. So in the end, what we obtain is two branches of solutions, or two bands, and this really is a formalism that is identical, very, very similar to the bands of the electronic bands of crystals. So this produces two bands. We give them names. So this one is basically what we call the acoustic, and this is what we call the optical branches of the band, or the two bands or the two branches of the phonons. And essentially, let's try now to understand what these two mean, and let's just look at the acoustic one first. When we have a very, very small q, that means a very long wavelength, and very, very long means compared to the lattice side, so the distance between atoms, or the distance between unit cells. And again, this distance is typically in the order of a few angstroms or nanometers in lattices, in materials, or the distance between atoms is a few angstroms typically. And wavelengths, for example, of sound are in the a few centimeters to many meters. So essentially, what we're seeing here is that for very for very long wavelengths, the frequency remains very low, so it goes down to zero, which we know the relationship is more or less linear. And what we obtain there is that the displacement of the atoms is basically, I'll try to draw here the lattice again. So we have the smaller atom, then the bigger atom, smaller one, the smaller one, the smaller one, and I'll just put a few. So in this case, all these atoms will, in the low frequency region, so over here, all of these atoms will displace in phase altogether, and this basically represents the existence of sound waves. So that's why we call these the acoustic branch. And these the motion of these atoms is essentially, I mean, you have long pieces of the chain or the lattice that move all together. Of course, if you go to one full wavelength, which is many thousands of atoms or many millions of atoms, you will have a piece of the lattice that is moving in one direction and the other one is moving in the opposite direction, and so on. But basically, is waves that are very long compared to the spacing between the atoms, and locally they all look like if all the atoms were moving, were vibrating in phase. As you increase the frequency or the wavelength, you reduce the wavelength, so you start getting close and close to the spacing between atoms. The motion of these lattice starts being, I mean, the motion is, the wavelength is shorter, so the chunks of lattice that are moving in phase get smaller and smaller, to the point over here, in this region over here at the end of what we call the first Brillouin zone. We have Brillouin zones here as well, in which one full unit cell will be vibrating against the next one and the next one and the next one. So what we will have here is that, well, this one moves in this direction, this one moves in that direction, and that's because the wavelength now is exactly one lattice site. So this means that while one pair of atoms in this case moves in one direction, the next pair of atoms will be moving in the opposite direction, so they will be vibrating like this. And in that case, of course, this one moves in that direction, and if we draw the next one, for example here, what we will have is that this lattice site will be vibrating in the opposite direction, and so on and so forth. So very long wavelengths essentially have big chunks of the lattice moving in phase, and of course, if you go to one full wavelength ahead, the chunk of lattice and these two chunks of lattice will be moving against each other, but they include many atoms, many lattice sites. In the other extreme of the first Brillouin zone, what we have is that the wavelength and the the wavelength of the vibration and the lattice position essentially vibrate against each other, and this is what we observe here. However, there are additional vibrations in this particular case. If we had only one type of atom, these would be the only possible solutions. So the unit cell is essentially comprises one atom. In this case, has two atoms, so it includes two atoms. So there are additional vibrations that we can think of. And these additional vibrations that we can think of are essentially the ones that are related to motions within the lattice. So another possibility is that these atoms are also vibrating. Now I will use a different color. So for example, that this atom is moving in this direction and this atom is moving in this direction, and the next atom will be moving in that direction and in this direction, and so on and so forth. Okay, this is a motion that can be excited by optical means, and this is a little bit harder to understand sometimes, but if you think of these two types of atoms as really two atoms that are different, and being different, there could be a dipolar moment between them, which if we have just identical atoms is not possible. So if we just have identical atoms in a straight line, we cannot distinguish between them, and therefore there is no charge distribution between one atom and the next one. But if we have two types of atoms, these one could be a bit more positively charged and the other one a bit more negatively charged, depending on how electrons are arranged and so on. And in that case, an electromagnetic radiation can produce these vibrations. So it can introduce the vibration of the lattice. And that's why we call this branch optical, because this one, the vibrations that involve complicated motions that are not just one full or many full lattice sites, but the motion of electrons within the site and involve the redistribution of charges within the unit cell are called the optical phonons. So in this case, we have this other branch of vibrations that also has this little bit of dispersion, is much less than the acoustic branch, and involves the motion of atoms that are different to each other. And this optical branch only appears when you have slightly more complicated unit cells, like this one, for example. Okay, there is another type of phonon vibrations that we haven't discussed, and we will not discuss in detail, but they are very, very similar in their treatment, and is what happens if we don't have just motions over the line, but more transverse motion. So if we have, let's imagine now the chain of atoms over here with their springs, and this atom is moving in this direction, and this one in this direction, and this one in this direction, sorry about that, and so on, or motions that are not just two consecutive atoms moving like that, but also, let's say, one atom, then the next one, then the next one, then the next one, and forming like a string that vibrates. Again, just thinking on a very simple unidimensional lattice. And essentially, these transverse phonons also exist, and we can do the math. It's not very different to what we already saw. And what we obtain is that there's, again, when you have two types of atoms and so on, you can have two branches, which are the acoustic transverse-optical phonon and transverse-acoustic and optical phonon. So in the end, we have more or less four branches, four phonon bands, if you want to call them like that, which correspond to the these ones are the longitudinal. So I will draw it like this: longitudinal-optical phonon. This is the sorry, no. Yeah. This is the longitudinal-acoustic phonon. Sorry about that. This is the longitudinal-optical phonon. And we will have the analogous transverse-optical phonon and transverse-acoustic phonon. And of course, the two different, I mean, the very low case, so the very long wavelength, low frequency case, corresponds to essentially acoustic waves moving along the material. And the high frequency end really corresponds to energy that is stored in these vibrations in the lattice, and that corresponds really to heat and so on. Now, if we think, all these analysis that we've done so far is essentially a classic analysis. So we've only used Newton's second law and a little bit of solving differential equations and so on. But we haven't treated these quantum mechanically. The quantum mechanical treatment of phonons includes the fact that the same as in the case of photons, where electromagnetic modes were treated as if they were harmonic oscillators. In this case, the vibrations themselves will be, and they are, because we are modeling these chains of atoms just like if they were essentially harmonic oscillators. The amplitudes, the amount of energy, so the amplitude of the motion that you can excite can only be excited in discrete amounts. And so there is a phonon energy which is related to the frequency. So for each one of these frequencies over here, so for each one of these frequencies, which all these frequencies, every single frequency is allowed in principle, unless we think of a finite lattice. But if we think of an infinite lattice, all the frequency values within the band here and all the frequency values between in these other band, they are all allowed in principle. And but for each one of those frequencies, you can only either give or obtain energy from in this case, from these elastic fields, if you want to call it like that, or from this elastic system. You can only give it or receive energy in quanta that also follows the same rule. So the energy of the phonons will be given by the rule h bar omega times n, which n is the number of phonons that we have excited, plus 1/2. So this means that even at 0 Kelvin, even in the absence of thermal energy, there will be a little bit of a vibration there of the lattice, which is just due to this n equals 0 minimum energy state of this elastic system, quantum elastic system. So with that, I think I want to conclude the phonon part. I hope this gave you at least an idea of how to treat now not just the electrons moving in the lattice, but the lattice itself, so the nuclei or the atoms, which can also move, and they are dynamic, so that they are actually having all these types of vibrations, and that also confer additional interesting thermal and optical properties to the lattice itself. Just for you to have a rough idea, phonons are typically in the few terahertz region, so they are compared to optical frequencies, so the visible or near infrared regions, they are much lower frequency. So optical phonons are typically in the few 1 to a few terahertz region for normal crystals, and it's always good to have a rough idea of where these phenomena happens. And with that, I want to conclude this session on phonons, and we will also talk a little bit about now other types of interactions that appear on crystals in the next session. Thank you very much.